Hi class, welcome to your final prior learning video in which we'll cover a new topic. This week we're going to talk about correlation and regression, specifically regression when we come together in class. But for your prior learning video lecture here, it's going to be all about scatter diagrams and this topic called correlation. Alright, so the objectives for the lesson today. I want to draw and interpret scatter diagrams. They're pretty easy. I want to describe the properties of what's called the linear correlation coefficient, so that's something new that we'll learn about in class. We'll compute and interpret the linear correlation coefficient, and we'll determine whether a linear relation exists between two variables. And then finally, I'm going to explain the difference between correlation and causation. And you guys might have heard the saying before, correlation does not always imply causation. And I'll give you some interesting examples of that. Alright, so let's go through the first thing. Let's draw and interpret scatter diagrams. Alright, so scatter diagrams have what's called first a response variable, and that is the variable whose value can be explained by the value of the explanatory or predictor variable. So there's an explanatory and response variable. Like for example, would you agree that your GPA can be somewhat explained by the number of hours of studying you do? So in that case, GPA would be response, hours of study would be explanatory. Okay, a scatter diagram is a graph that shows a relationship between two quantitative variables measured on the same individual. Like me, for example, the GPA and hours of study would be two quantitative variables. All right, each individual in the data set is represented by a point on the scatter diagram. Okay, the explanatory variable is plotted along the horizontal axis, so the x-axis, and the response variable is plotted along the vertical axis, the y-axis. Okay, here's an example. All right, the data shown to the right are a study based on study for drilling rock. Okay, so researchers want to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So for example, what they're suggesting is if you're closer to the surface, to drill 5 feet would take you less time perhaps than if you were further down. Like let's say if you look down here like at 190 feet. Alright, so depth at which drilling begins is the explanatory variable x, and the time in minutes to drill 5 feet is the response variable y. Alright, let's draw a scatter diagram for the data. So basically, if you look, you have x, y points right here. These are all my x's, and these are their corresponding y variables. Alright, if you plot them in a scatter diagram, it looks like this. This is the depth at which they tried to drill 5 feet, and this is the time it took in minutes. Well, let me ask you this. Just by looking at it, does it look like there's some type of relationship? It's not perfectly linear, but maybe as the depth increases, the time it takes to drill also increases. That seems to be the general trend of the data. So the scatter diagrams tell us a lot. All right, they tell us about the relationship between two variables. And if you look here, here are some various different types of the scatter diagrams and what they tell us. This, all right, this is an explanatory. All right, as the x variable increases, so does the y. Here's another one. It looks kind of straight. This is also explanatory. So as x increases, y actually goes down. Both of these are a linear relationship. Things do not always need to be linear. Like if you look at this scatter diagram here, kind of looks like the parabola perhaps. That's explanatory. It tells us that the relationship is nonlinear. Same with this scatter diagram here, nonlinear relationship. And believe it or not, if you look at this, right, even though it's just a bunch of dots randomly and doesn't really seem like there's much going on, that is explanatory. It tells us that there's no relationship between the two variables. Right? So no matter what a scatter diagram looks like, it can tell us something. Alright, two variables that are linear related are positively associated when the above average values of one variable are associated with the above average values of the other variable. And below average values of the variable are associated with the below average values of the variable. Okay, I'll explain that. That is, two variables are positively associated whenever the value of one variable increases, the value of the other variable also increases. Like this. This is positive association. When the x variable increases, so does the y. Well, if this is positively associated, what do you think this will be? Well, it'll be negatively associated. Two variables are negative associated when above average values of one variable are associated with below average values of the other variable. That is, two variables are negatively associated whenever the value of one variable increases, the value of the other variable decreases. So like this, negative. As x increases, y actually goes down. So just like how you think with a line, this is positive slope, positively associated. This is negative slope, negatively associated. Okay. Let's describe the properties of what's called the linear correlation coefficient now. All right, so what we want to do is we want to measure the strength of relation for linear relationships, like these two scatter diagrams right here. Like, how strong is this relationship? How strong is this one? Like, it's one thing to just look at the graph and say, oh, hey, yeah, that looks pretty positively correlated, or that looks pretty negatively correlated. Like, we want to put a mathematical number to it now. Okay, so the linear correlation coefficient, or it's also called the Pearson's product moment correlation coefficient, but we'll just call it the linear correlation coefficient, is a measure of strength and direction. So direction also tells of linear, and this is important, it only measures linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, which we won't actually use that much, but we'll use this R right here. So letter R represents the sample correlation coefficient. So I'm going to present only the formula for the sample correlation coefficient, and it's this right here. It looks like a crazy, crazy formula. All right, so the correlation coefficient is we're going to sum up each x individual value minus its average divided by its standard deviation. I'm going to multiply that by each y variable minus the average of the y's divided by the standard deviation of the y's. So I'll do this for each one and then multiply them and then sum it up for each value. And then I'm going to divide by the number of individuals in the sample minus 1. You might remember seeing that. That's kind of like the degrees of freedom of n minus 1. This is an incredibly complicated formula, and actually I'm going to do an example with you in a second that shows you how crazy it is, but we're actually never going to do it by hand because it takes too long. All right, so here are some properties of this value R right here. There's a bunch of them. First one, the linear correlation coefficient is always between -1 and 1 inclusive. All right, so that means R can never be like -2 or 3. It's always going to be between -1 and 1. So like -0.75 or positive 0.6. It's going to be between there. All right, if R is equal to +1, there's a perfect positive linear relation between the two variables. So that means it follows a perfect straight line going up. Similarly, if R is equal to -1, then there's perfect negative linear relation between the two variables, so it goes straight down perfectly. The closer R is to +1, the stronger the evidence of positive association between the two variables. And then similarly, the closer R is to -1, the stronger the evidence of negative association between the two variables. All right, so positive numbers, positive correlation, so let me go back. That means this. All right. Values close to -1, it means this type of relationship. Okay. 6, if R is close to 0, there's little or no evidence of a linear correlation between the two variables. All right. So R close to 0 does not imply no relation. It is important, just no linear relation. Like, forgive me for going back. But like this one right here, this would have an R of 0. It's just saying there's no linear relation, but there's definitely a relationship, just the linear correlation coefficient doesn't pick it up. Okay. All right, the linear correlation coefficient is unitless measure of association, so there's no unit of measure for x and y so the unit of measure for x and y play no role in the interpretation of R. Okay, so if it's x is in feet and y is in feet, R is not in feet. It's unitless. All right, important here, the correlation coefficient is what's called not resistant. Therefore, an observation that does not follow the overall pattern, so like a huge outlier or a really skewed data value, could affect the value of the linear correlation coefficient, and quite heavily, actually. All right, so here are just some sample ones. This is R is equal to 1, positive, perfect linear relation. Here's 0.9. You can see it's a little bit more spread out, but you'd see the definitive pattern. Here, R is equal to 0.4. All right, you can see the pattern for sure, but it's a lot more spread out than it is over here. Similarly, the flip side, here's -1, -0.9, -0.4, getting more spread out. Here is R is equal to 0, no linear relation. The data is just like all over the place. You can't really see a relationship. This is also R is equal to 0, but you can see that there's a definite relationship, just the linear correlation coefficient won't pick it up. All right, here's an example. If you kind of just think about this, all right, here's y bar in the middle, here's x bar in the middle, all right? Below values of x, below the average values of x are associated with below values of y. Above average values of x here are also associated with above average values of y. So this is that positive association right here, positive linear association. All right, let's compute and interpret the linear correlation coefficient. All right, so if we go back to that example about drilling, all right, the depth at which drilling begins and how long it takes to drill 5 feet. I did this one in Excel for you guys here, and as you can see how complicated the formula is. So for all the x values, I computed the average, and this is the sample standard deviation. Same thing for the y. Here's the y average. Here's the y sample standard deviation. So this number right here, I took the depth, 35, minus 126, then divided by this. To get this number here, I took 50. I subtracted this, divided by this. And I did that for all the x's. Then for the y's, like this y value right here, I took 5.88. I subtracted away the average. Whatever that number is, I divided it by the standard deviation. I did that for all the y's. And then the formula tells me to take this value and this value and multiply them. I did that for all these. And the last thing I did was I summed it up, and I got this. Wow, crazy complicated. I would not imagine wanting to do this by hand. Well, that sum here was 8.50. So I replaced in my formula this crazy thing with this number right here. There were 12 observations, so I divide this by 11, and I get this right here. The good news is we come together in class. I'll show you how to calculate this using our graphing calculator. So don't stress so much if this looks incredibly complicated. We'll actually do a shortcut and use technology to get it very easily. All right, so let's determine whether a linear relation exists between the two variables now. All right, there's got to be a cutoff. Like, wow, this is great. This number is 0.773. All right, that implies that there could be positive linear relationship or linear correlation between the two variables, but we need a statistical method for approaching to confirm that. All right. So first off, determine the absolute value of the correlation coefficient. All right. Step 2, you're going to find the critical value in Table 2 from Appendix A for the given sample size, and I'll show you that table in a second. And then Step 3, if the absolute value of the correlation coefficient is greater than the critical value, we say a linear relation exists between the two variables. Otherwise, there's no linear relation. All right. So here we're going to determine if there's a linear relationship. This is what Table 2 looks like. Here's our sample size. All right. Well, if you look back for this problem here, the sample size was 12 right here. So you'd go to 12 along the n value, which is right here. And here's the cutoff value. All right. So if our correlation coefficient, which was 0.773, is greater than that number, which is 0.576, all right, we can say for sure there's a positive linear relation between the two variables. So between time to drill 5 feet and depth at which the drilling begins. So you look at the sample size, you get the cutoff value. If you're above the cutoff value, you can say there is that linear relationship. All right, the last thing I want to talk about real quick is explain the difference between correlation and causation. All right, let's take a look at this question. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Whoa, that's a really high correlation. Does that mean that there's causation between getting a bachelor's degree and births to unmarried mothers? Right? So does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of birth to unmarried mothers? All right? Certainly not. Certainly not. The correlation exists only because both percentages have been increasing since 1990. All right? This is the relation that causes the high correlation. Okay, so in general, time series data, so data collected over time, may have high correlations because each variable is moving in a specific direction over time. All right, so both going up or down over time, one increasing while the other is decreasing over time. All right. So when data are observational, like this, like we just observed the data, all right, we cannot claim a causal relation exists between two variables. We can only claim causality when the data are collected through a designed experiment. And collecting this data here about bachelor's degrees and unmarried births, all right, was an observational study, not a designed experiment. All right, another way that two variables can be related, even though there is not a causal relationship, is through what's called a lurking variable. All right, a lurking variable is related to both the explanatory and response variable. So it's like behind the scenes affecting both. All right, so for example, ice cream sales and crime rates have a very high correlation. Okay, does this mean that local government should shut down all ice creams? No. Here the lurking variable, the variable behind affecting both, all right, is temperature. as air temperature rises, both ice cream sales and crime rates rise. So that lurking variable is actually what's causing the high correlation between ice cream sales and crime rates. Here's another example. All right, because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers Catherine L. Tucker and associates wanted to know whether cola consumption is associated with lower bone marrow density in women. All right. The table lists the typical number of cans of cola consumed in a week and the neck bone mineral density for a sample of 15 women. Okay, so this is the number of cans that of cola they drank per week, and this is their bone mineral density. All right, the data were collected through a prospective cohort study. All right, so it was a designed experiment here. All right, the figure on the next slide shows the scatter diagram of the data. So this is what it looks like. So you can see it looks like there's a relationship here. It looks like as you increase colas, your bone marrow density goes down. Yikes. All right. So the correlation number, if we calculated it between the two variables, is negative 0.806. So the critical value for n is equal to 15 from that table. Let me go back there. All right. Oh, it's not on here, but if you look, n is equal to 15 on that table. All right. Was 0.514. So because the absolute value of our correlation is greater than that, we can conclude that a negative linear relation exists between the number of colas consumed and bone mineral density. But here's the thing. Can the authors conclude that an increase in the number of colas consumed causes a decrease in bone marrow density? I don't know. Could there be some lurking variables in this study? So something behind the scenes affecting it. All right. So, in prospective cohort studies, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, data are observational. So, the researchers cannot claim that increased cola consumption caused a decrease in bone marrow density. All right, here's why. Some lurking variables in the study that could confound the results. Body mass index, all right, your height, your smoker, alcohol consumption, calcium intake, physical activity. All these things could affect your both consumption of colas and your bone mass density. All right, so there's lurking variables behind it affecting it. All right, so the authors were careful to say that increased cola consumption is associated with lower bone marrow density because of those potential lurking variables. All right, they never stated that increased cola consumption causes lower bone mineral density. All right, when we come together in class, we'll talk about how you calculate, and I'm going to go back and show you this. All right, with your calculator, so it'll be really easy. We'll never have to do any of this. And we'll also draw some more scatter diagrams, and we'll actually talk about regression. All right.